let's do something different. So I've been doing a lot of normal mode stuff, so masses on springs and finding normal modes. And I did this. These are three masses connected by springs, and I wanted to find the normal mode. So what are the normal modes? The normal modes are the conditions you can start for this system such that these all oscillate with a constant and same frequency. And who cares about normal modes? Well, one, they look cool. Number two, any other solution can be made as a linear combination of normal mode solutions. So that's kind of useful. And I did this problem already. Okay, so the way you do this, the way you find those normal modes is essentially you write down equations of motions for these three masses, m1, m2, m3, using variables x1, x2, and x3, and we can get this matrix, I'm going to call it the K matrix, which I wrote, shifted down because I didn't want to write it more than once. And that's basically, if I write this matrix, then I can write a vector solution for all three masses, x1, x2, x3, as this vector. So they all have some different constants in front of them, but they all have the same angular frequency of oscillation. So that's the same solution for them. And then if I take the derivative of that twice, I get an omega squared. And then so what this says is that this matrix operated on this solution should give that solution back with an omega squared. And that's where this comes in. That right here. So this says that matrix K multiply, I'm using this line through it for my matrix notation. Everyone does their own thing, I do my thing, so, multiplied by that vector gives the same vector back with a constant, a scalar constant. In this case, that scalar constant is omega squared. Now, in the previous video, what I did was to use the eigenvalue problem. I used the linear algebra feature in NumPy to find that. But I want to do it a different way, because although I like NumPy, I like WebVPython too, and so I thought it'd be fun to come up with a new way of finding this. So this is the key here. I have some vector, and I operate it with this matrix, which I can find that matrix. These are just numbers, right? K1, K2, M1, these are all numbers. This is a 3x3 number matrix. If I do that vector matrix operation, I get another vector. I can do that. And so the question is, can I just move around this vector A? I'm going to change this vector A until I find one that's in the same direction. That's exactly what I'm going to do. Okay, so I have a couple things in here, and I've done this before with the moment of inertia tensor. But the first thing is, how do you make a matrix in WebVPython? I'm going to say the matrix K, I'll call it like that, K, is just a list. I'm going to call it KX, KY, KZ. Oops, that's a list. And KX is a vector. And that would be, K1 plus K2 over M1, and then whatever that negative K2 over M1, 0. That's my vector, right? So each of these are vectors of the matrix. So right here, I'm going to call this KX, KY, and KZ. And then if I have a matrix like this, I already made a matrix multiplication function, KX1, KX2, KX3. These are capital Ks. KY1, KY2, KY3, KZ1, KZ2, KZ3. That's a Z, and that's a 3. And then if I have the matrix A, let's call it A1, A2, A3, I can easily do this, right? Because I'm going to get this answer, which I'm going to write as a column, but it doesn't really matter. This first product right here is going to be equal to A, the vector A, dot KX, right? Because here's the vector A, here's the vector KX. It's just the dot product, which we already have built into WebVPython. Awesome. And this is going to be A dot KY, and this is going to be A dot KZ. So I can do this, and I can see, now is this the same, in the same direction as that? So now the next question, how do you know they're in the same direction? There's a couple things. In the past I did, let's call this AK, because it is. So is AK in the same direction as A? It doesn't have to have the same magnitude. Well, one thing you could do is do the dot product AK dot A, and that's going to be equal to the magnitude of AK times the magnitude of A times the cosine of the angle between them, and then find the angle. But you don't need to do that when I can just do, if they're in the same direction, then AK cross A is equal to the 0 vector. So I can take the cross. So what I'm going to do is find a vector. This is my vector. I'm going to operate it on my K matrix. And then I'm going to take that new vector, which is this, and take the cross product with the original vector and see if it's 0. If it's 0, then I just found a normal mode. Now, but how do I find all these vectors? Am I just going to randomly do it? That's not a bad idea. I was thinking of kind of like, since this is a vector, just kind of moving this through space. But I think I don't actually need all 3 components. I only need 2, right? I only need to change 2 of them because it doesn't matter the magnitude of this vector. It only matters about essentially the direction. I could normalize it. You only get 2 components. So what if I say this? What if I say the vector A is, I'll write it as a vector A1, A2, A3, and then I use spherical coordinates to find A1, A2, and A3. So let's say R is 1, the radius of this vector is 1, and then I can use my normal spherical coordinates where I have, this is the z-axis, and this is my R, and that's theta, project this down, and that would be phi. So A1 would be R sine of theta, cosine of phi. A2 is R sine of theta, sine of phi. And then A3 is R cosine theta. So I can find those. All I need to do is now change thetas and phis and just see what happens. So what I'm going to do is actually pick a value for theta and then have my phi go all the way around 2 pi and then increase theta and do that so forth. So I'm going to increase theta and then increase phi and then just make a double loop and go over it. So I'll go through all of the possible spaces. How's that sound? Okay, let's jump over here to Python. I've already got started. Let me show you what I have. So is that big? That's not big enough. I know that's not big enough. I'm going to make it bigger. That's bigger. Okay, we like it like that. So here's my M1, M2, M3, K1, K2, K3. Let me point out that this I already know the answer because I'm going to check it, right? So if I go to the way I did it before, this is Google Colab where I actually take the eigenvalue. These are the same values right there. It's the same K function, and then I use the eigenvalue sub function. I don't know what it's called. And I got my A values down here, so we can check. So we're going to check that. But let's just do it the first way. So I've already got my M1, M2, M3, K1, K2, K3, K4. Here's my KX, KY, KZ vector. And then I combine those together to make my K matrix. And then I print. I'm going to run it print K. And then this is my matrix multiplication function. So this takes the matrix A, and it assumes it's a 3 by 3, and the vector B, it assumes it's a three-dimensional vector. Okay, I didn't do this a great way. I did it the way that works. And so just like I said, I'm going to get a resultant vector C, and it's going to, the X component is going to be A, the first vector in A0, that's the first in the list, dot B, and then that's going to be the second vector dot B and the third vector, and then returns it. That's it. Let's just try this and see if it works. I'm just going to pick a value for A. So let's say A is equal to the vector 1, 0, 1. That actually might be my value. I think that is. No. Yeah, because that would be, no. It's not. If negative 1, 1 is, I think. I'm pretty sure. So let's just print out that, and then we'll manually take the cross product to see if how that works, and then we'll start doing our subroutine stuff. So let's just say C is my new vector, and that's going to be M dot, the vector, the matrix K, and the vector A. And then I want to, let's print C. Let's just do that. Let's just see if it works. Okay, so that did work Okay, so there's my vector C. It's not in the same direction as A. We could test that by saying, let's print. I don't want to call that C, but let's just print what cross product of C and A. That's going to be A cross C. And if it was 0, if 0, 0, 0, then it would be an eigenvalue, and you see it's not. Okay. Now, one of the things I might want to do, I am going to do, is I'm going to do norm, right? Because I don't really care about the eigenvalue omega right now. And that'll just make things more well-behaved. It would be between 0 and 1. And now, I think, oh no, it's not. It's not an eigenvalue because I have different masses. Okay, that's fine. Let's just jump to it, right? Let's just get started. Okay. I don't need this. What I want to do is I'm going to start with a theta and a phi. So theta equals 0, phi equals 0, d theta equals 0.01. We can change that later. D phi equals 0.01. So this is the how much I'm going to change theta by, how much I'm going to change phi by. I'm going to go ahead and make a graph because it's kind of hard to make a graph. I'd like to make a 3D graph, right, of theta versus phi, and then have the cross product in the z direction. But we can't. This doesn't do 3D. It does do 3D, where the third dimension is time. So I'm going to make an animated graph. So let's put our graph. I like to put my graphs at the top. G1 equals graph. Let's see. I'm gonna plot theta versus the cross product, which I'll call C. I'm going to call the other thing something else. So let's say the x title is going to be equal to theta. And then what I'm going to do, let me tell you what I'm going to do. And then I'm going to say y title, let's just call it C. And then let's say width is 500, height equals 250. Now I need something to plot. We'll call it F1. F1 is G curve. Color equals color dot blue. Now, what about phi? I'm going to plot C versus theta. And then I'm going to change phi and do it again. So I'm going to animate it in the phi dimension. Does that make sense? And animated graphs are actually very easy in WebP and I think they're kind of nifty. Okay, so we're down here. I got my stuff. The first thing I'm going to do is now let's go ahead and make a loop. So while theta is less than pi, remember theta just goes from 0 to pi, and I need to put a rate here. If I want to animate it, I need to say how fast to do the animation. So this tells it to not do more than 100 loops per second. And now in this loop, I'm going to reset phi to equal 0, right? Because I'm going to show you why. And I'm going to do this. F1 data equals an empty list. So in order to make an animated graph, we're going to actually add all the data to a list and then plot that list. But every time I do it, I have to restart and I have to empty the list. So I emptied the list. Now we're going to make another loop inside the loop, a loop inside of a loop. And that's going to be like this, while phi is less than 2 times pi. Right, so we're going to go through 0 to 2 pi and phi, and then increase theta 0 to 2 pi, increase theta 0 to 2 pi, and keep doing that. I don't need to put a rate statement here. So what I'm going to do is to calculate ax, ay, az. So let's go ahead and put, let's say r equals 1. Ax equals r times sine of theta times cosine of phi. You got to spell it right. Ay equals r times sine of theta times sine of phi. And then finally az is equal to r times cosine theta. That's it. Now I'm going to make my a vector. A equals vector ax, ay, az. And then now I'm going to take the dot product. I'm going to do it all in one step. I want to find the new vector, k dot a, and then take the dot product with a, the cross product. Okay, and I'm going to call that c. So c, I like this up a little bit higher. C equals the cross product built into WebVPython, A, and then the other vector is going to be m dot times of ka, right? So that's a dot product between a matrix. Now, like I said, I want to normalize this. So if I do norm, that will make sure that that vector has a length of 1, so things don't get out of hand. A already has a vector of length of 1, so the cross product A cross the other thing shouldn't be greater than 1. So I'm limited down to 1, so that just makes things more well-behaved. Okay, so I have my value. Now I want to add a data point to my graph. F1 data equals F1 data plus the x value, which is going to be phi, and the y value is going to be the magnitude of c. I can't plot c because it's a vector. And now I'm going to increase the value of phi, or this loop will go on forever. Phi equals phi plus d phi. And then I'm going to end the loop. When I end the loop, I'm going to plot that function. So I'm going to say f1.data equals fdata. So f1 data. So that's how the animated thing works, right? You make an empty list right there. You add your data points to the list. And then when you're ready to just plot the whole thing at one time, you just say f1.data. That's the name of the graph. That's the .data. And then I give it my data file. That's it, and it plots it. Now, before I go back up, wait, this is all shifted. This should be there. How to get out of whack, I don't know. Now what I need to do before I go back up here is increase my value of theta. Theta equals theta plus d theta, or it won't work, right? Because it's going forever. And so you see here at the end of this loop, I'm at phi equals 2 pi. So I need to go back up to phi equals 0 when I redo the next loop, and that's what that is right there. Whew. Okay, let's see if that actually works. Probably we should save it. Saving is a good idea. Now I'm going to run it. Okay, it looks like it's working. I'm looking for where that graph touches the 0 points, right? And it's fast and everything like that, and that's fine. We can fix this a little bit better. Okay. So let's make that graph nicer. So I'm going to put y max equals 1. That way it kind of like zooms in and out. See, that's beautiful. See, I don't know the value of phi when it touches, but I know that it is touching, or at least getting close to touching. Those are my eigenvectors. I just need to find those now. How can we do that? Well, how about this? All I need to do is to test if c is some small value, then just print out the value of a. That's one way to do it, and that's what I'm going to actually do. So down here, I calculate c. And then let's put it down here at the bottom. No, let's put it right here. If mag c is less than, I'm just guessing, 0.01, maybe that's not small enough, then let's print a equals vector. No, let's print out a. That's it, right? I already have the a. I don't need to know what theta and phi are. I just need to know a. And it should be normalized. So if I don't get any values of a, it means my limiting factor here is too small. If I get a billion values of a, it's too big. So let's just run it and find out what happens. Okay, so you'll notice that it's like jumping. And that's okay. It's jumping when it gets it. So I'm getting like 3 or 4. Let's make it a little bit smaller and see if we can get it to work a little bit better. Let's do this half as big, 0.5, and run that. And then we can test those values. Okay. So let's go up here to the, is it done? Let's wait till it's done. Impatient. I think it's done. Okay. So up here, these first 1, 2, 3, 4 values are all, maybe even 5. These are all the same. There's way too many there. No. Yeah, so let's make it a little bit smaller. 0, 1. I'd rather get too few than too many. It just looks bad. It's just bad form. See, now I'm not getting any. That's all the stuff I had before. Okay, so let's make... You can't get everything, can you? 2. I should get at least 1 this way. I'm just guessing. Nope. Okay. 3. There we go. Okay, we're getting 4 at a time. That's fine. It's good. So let's go up here to this first one. Maybe, I might have my d theta d phi too large, but it's going to be good. It's proof of concept. It's just for fun. It'd be much better to do it with the eigenvalue function before. So let's look at this first one. 0.1, negative 0.29. Oh, I need my other program. Let's see. Because I have that mass program. Let me see if I can open this up. See if I can find that. My trinkets. I had it up here. Here, this is it. So let's see. I can put in my values and just see if it works. That's the first thing I'm gonna do. But the first thing is I need these values the same as what I have in my other code, right? So I need. I'm gonna have to delete that. So I need these. I think I can just copy this. Or let's see, that's 12. I think that's the only difference. 0.15, 0.15, 0.1, 10, 5, 5, 12. Yeah. Okay. So now let's run the other program. Let's run this and get that value of A and put it in for my initial values for x1, x2, and x3 and see if it gives a normal mode. I just like the graph. I'm just happy with the graph. I don't care if it works or not. That graph is just kind of cool. So I'm going to go up here and just copy this. That's that first one. I should probably take the middle one because that one. And then going back up here, and I'm going to say, I'm going to put it down here, x1 equals this number, x2 equals this number, x3 equals that number. And then I'm going to comment out these, even though you don't have to because I'm changing them anyway. And let's see if it looks like a normal mode. Okay, so it's too big. So it is a normal mode, but it's too big. So I need that S factor in there again. So the S factor just said, scales it down a little bit. I don't want to have everything going too large. It's just no fun. So S times, S times, S times. It's still a vector. I can multiply by a constant. Okay, so it looks like it's working, right? They're all moving in similar frequencies. I have the graph down here, right there. Yep, that works. That works. Now, what if I had more degrees of freedom? What if I had 5 degrees of freedom? I could make a 5-dimensional vector. I'd need to change 4 properties of it. And then, so the question is, how do you do that? I mean, you could just use just change x's and then change y's and change z's. But it's not, you'd have to change all 3 really. Okay, that was fun. I actually have I just came up with another idea of a way to visualize this. I think I might make that in another video. But I'll put a link down to my other normal mode videos below in case you want them. And that's that. Talk to you later. And the code for this normal mode thing, because it's fun. And the animated graph. Okay, bye.